So I'm going to talk about coping with NP-hardness. I will start by giving some motivation for this kind of work or where they occur, and then give some examples of the kind of things which I do. So optimization is ubiquitous. And for example, look at the kidney exchange problem, where the objective is to maximize the collective benefit of given pool of incompatible pairs of incompatible pairs of patient and donors. And we usually measure this optimization by how many number of patients we are able to match. Or look at this container placing problem, where you would like to place the containers in a way that when you unload these containers from the ship, as I said, which are quite ubiquitous. For example, look at a place and you like to guard this whole region, and you want to place minimum number of cameras so that you can guard all the place. Or you like to place the chips on a chip so that the amount of wires which you use is minimized. Okay, so these are the optimization problems which are quite ubiquitous and they occur quite naturally in day-to-day life. Okay, unfortunately, most of these problems are NP-hard. And what do I mean by they are NP-hard? There is no algorithm which can solve all instances optimally in polynomial time. I hope to answer, give you explain you each of these terms throughout this talk. So first of all, let me explain what do I mean by polynomial time. Polynomial in what? So what I mean by this, polynomial in the input size. So for example, for the kidney exchange mechanism, the input will be number of patients and number of donors. So you like your algorithm to run polynomial in number of patients and number of donors. Similarly, for the guarding problem, your input is the area. So say n square unit, how many, and you want to place minimum number of guards, and now you're trying to run an algorithm which is polynomial in this n. So this is what I mean by when I say polynomial in input size. Okay, so now what are the ways people have deal with coping with hardness? So as I told you, no algorithm solves all instances optimally in polynomial time. So what we could do is that we can forego the idea of solving the problem on all instances and restrict the kind of inputs we are looking at. Or this is what leads to the field of parameterized algorithms, which I will talk a little bit in more depth. And what I mean by optimally is like, okay, I forgo the desire of, say, finding the solutions optimally. For example, for the guarding problem, suppose the minimum number of camera we need is 15. I don't care with 15, but I'm happy with even if you give me 20. So this is like a factor 2 approximation with respect to the optimum. And in polynomial time, we forgo the idea of amount of running time, which we allow from polynomial to exponential amount of time. So let me start with an abstract problem, what is called vertex cover. So here you are given a graph. So what is a graph first? Let me tell you what a graph is. Graph essentially consists of nodes, and there are some links between them. So all these circular things which you see, they are nodes, and the edges or the links between these two nodes are called edges. So it has a lot of modeling power. For example, if you wanted to arrange a meeting and you only want to bring people who know each other, then you can model the people by these vertices. And if they don't know each other, you can put an edge between them. So then you are looking to find a set of people. You want to move or delete small number of vertices from the graph so that every edge is covered. So for example, in this graph, what are we looking for? We want to have minimum number of nodes such that every edge has one endpoint in it. Or in other words, you have two side sets and you want to find small number of points such that from every set, there is at least one point. So in this graph, there are 40 vertices and there are 40 edges. And we ask ourselves, can we have a vertex cover of size 5? Well, let's try to see why we cannot have 5. So there are I have made 6 red nodes, and notice that for every red node, there's an edge with one black node, which is private to it, which means that whatever be the solution, I cannot hope to get a 5 size solution because there are 6 edges which are pairwise independent, vertex independent. So for 5 vertex, this is not an answer. But if you look at for k equal to 6, this is an answer because you now look at these red vertices which are 6. they do form an answer, because for every edge you can think of, there is one node which is colored red. Okay? So this is what is called classically a vertex cover problem. So what I've told you, you're given a graph G, integer K, and the question is there a vertex at S such that mod S is less than or equal to K, and every edge has at least one endpoint in S. So as I told you, this helps in removal of data items to resolve conflicts. For example, it is also used in protein-protein interaction where like nodes forms proteins, and if there's an interaction, you put an edge between them, for example. But I will be looking at it from the graph theory point of view, and our objective is to find K vertices whose deletion keeps the graph edgeless. And what I mean by deletion in a graph, when you delete the vertex as well as all the edges which are incident to it. So of course, there is an algorithm to find minimum size vertex cover, is that you try all possible subsets, which does all possible subsets, and test whether after deleting that graph contains an edge or not. If it is not, then this is a potential solution, and you can return check if there is one of minimum size by going over all subsets of size k of n. That will give you upper bound of 2 power n. But since we are only interested in solutions of size k, there can be an algorithm which is runs in time n choose k, and then you test whether that forms a solution or not in polynomial time, leading to this algorithm with running time n to the power k plus 2. But what are parameterized algorithms? It's often reasonable to assume that k is small compared to the input size, which is big N. So for example, n is 1000, k equal to 20, n to the power k is way too slow. And the question is, can we do better? Can we narrow down this search space? Do we need to look at all solutions of size k to find one of size k, or we can be smarter? So here's one way to be slightly more smarter. What does it mean to put A into solution? So whenever you put A into solution, you can delete A and all the incident edges and decrease k by 1. And so here's a faster vertex cover algorithm. You know, from every edge UV, at least one of U and V must be in the solution. So G has a vertex cover of size at most k, if and only if G minus U has a vertex cover of size at most k minus 1, or G minus V has a vertex cover of size k minus 1. So you look at an edge and recursively try to get a solution either containing U or either containing V, and output the one with the minimum size. Now you recurse, because now you have got a smaller instance because you have deleted a graph, smaller parameter because now you are not looking for a solution of size k, but rather looking for a solution of size k minus 1. So this is how you can get a recursive algorithm. And the running time analysis will be that initially you had one instance with G comma K, then you created two instances, one with K minus 1, another with another parameter K minus 1, and you can go on and doing this. So this search tree will have total number of nodes, roughly 2 power K, and at each node you take polynomial amount of time, leading to an algorithm with running time 2 power K into n plus m. So now there's a notion of XP versus FPT. What is XP? Is like n to the power k plus 2. It's like polynomial for every fixed k. Versus, this is called slice-wise polynomial. And there's another one, which is 2 power k into n plus m, which is same polynomial for every k. So for example, in the left side, if I put k equal to 3, it is n to the power 5 algorithm. But in the right side, if I put k equal to 3, it is still some 2 to the power 5 times n plus m. So it's a constant times n plus m. So we are basically trying to design an algorithm which dependence on k could be exponential, but the dependence on the input size should be polynomial, some n to the power c. And this is what is called fixed parameter tractable algorithm. So these are like bad algorithms, and the right-hand side are good algorithms. So what is parameterized algorithms designer question ask? First we ask, is it FPT? That is, does there exist an algorithm with running time f of k poly in n? Can we do better? So by better mean, can we get smaller f of k? Can we get smaller n to the power c? Or can we get both best of the both world at the same time? So these are the kind of questions we ask in this algorithmic paradigm to deal with NP-hard problems. So another problem which we worked on was like bisection. So you're given a graph Z and you want to partition into two equal parts with at most k edges going on inside. So this is a classical problem. And why it is important? Because when you are able to balancedly decompose your graph into two parts, a lot of problems can be solved appropriately by using a paradigm called divide and conquer. And that allows us to do nicely. But unfortunately, there's an easy n to the power 2k plus big O of an algorithm. But is this problem APT? It was open for quite a long time. And then we gave an algorithm of this nature with running time 2 to the power big O of kq by coming up with a graph decomposition, which is useful in many other settings too. So that was all about parameterized algorithms. And to know more, one can look into this book, which narrates the recent developments. So let me move to an approximation algorithm, which is the second field which I wanted to talk a little bit about. That what is a two approximation algorithm? So for two approximation algorithm, for every instance, I want to find a solution that is at most 2 times as bad as the optimal solution on that instance. For example, for vertex cover, we want to find a set S such that the size of S is not more than 2 times opt. So here's my algorithm. While S is 5, and while G minus S has an edge UV, you add S equal to S union UV. So let's look at this. So A and B is a minimum size vertex cover, but first we'll pick an edge AE and add AE to my solution. Then all the edges incident to A and E will be deleted. Then we'll pick an edge BC and pick both vertex B and C to our solution. Then what happens? At each iteration increases cardinality of S by 2 because we are adding 2 solutions. But notice that S intersection opt also decreases by at least 1, which means that every time when I pick 2 vertices, optimum solution has decreased by 1. So number of times we can run this iteration is opt times, and each time we are adding 2 vertices, so this is twice opt. And this is not the only kind of deletion problem which people have studied in the literature. So this is like deletion to a dependent set, deletion to, so you can delete vertices to get a special kind of graphs called forest, or planar graphs, a graph which can be drawn in the plane without making the edges cross, or series parallel graphs, or interval deletion. And there are plethora of such problems in the literature. And the next question is, which vertex deletion problems are NP-hard? And already late in 1980s, Lewis and Yanakaki showed almost all of them. And from that time, there was an important question in the area, which have constant factor approximation algorithms. And we answered in 2012 that actually many of these problems do have a constant factor approximation algorithm. And what we proved is that vertex deletion problems, which are classes which are closed under vertex deletion, means solution does not increase by deleting a vertex, solution does not increase by deleting edges, solution does not increase by edge contraction, and excludes some one plane graph, then has a constant factor approximation algorithm, which basically means that vertex deletion problems which are closed under minor closed operation has a constant factor approximation algorithm. For example, a cyclic graph. So basically we said that all these problems are minor closed, and all these problems excludes a planar graph, and hence they have a constant factor approximation algorithm. How did we design our approximation algorithm? So a randomized 2 approximation for vertex cover could be, while S is not a solution, pick a random edge UV in G minus S, pick a random vertex in U comma V, and add S equal to S union X. What is your main observation? So whenever you pick an edge in G minus S, there's a probability half that one of these endpoint will go into the optimum solution. So in expectation, after every 2 rounds, every twice, you have reduced the optimum by 1, leading to a factor 2 approximation algorithm. So our approximation algorithm is also as simple as this. While S is not a solution, we apply some cleaning operation, and then we pick a random edge, pick a random vertex, and put into the solution. The main observation is that X is an optimum solution to G minus 1, G minus S with probability 1 over C, and that requires hard work. But this cleaning operation requires playing techniques based on automata theory, logic, and other mathematical notions, and it forms the most technical part of this paper or article. So I will talk a little bit lastly about exponential time algorithms. So naive vertex cover, as I told you, is 2 power n algorithm. The question is, can we do better? So already in 1976, these questions was considered by Tarjan and Krusonsky, and they gave an algorithm with running time 2 to the power n over 3, which means 1.26 to the power n. Like improving 2 power n to 2 power n by 3 is like improving order n cube to linear time algorithms. And this talk, I will tell you a little bit of algorithm which runs in time 1.5 to the power n. So here's my simple algorithm. I look at k and n. I look at their ratio. I check, Is k by n less than half? Hello?
Yes, you have 3 more minutes.
Yes, I will be done.
Sure. Yes.
Okay. So if k by n is less than half, I run the 2 power k time algorithm, which I already told you in the beginning. If k by n is more than half, we uniformly at random pick a vertex in our solution. So basically, when we are saying that if the size of the solution is too small compared to the number of vertices, then run that FPT algorithm. If the size of the solution is too large compared to the number of vertices, putting a random vertex into the solution leads to you have a good chance of picking them into a solution. You delete it and decrease k, you analyze, and you get a running time algorithm with running time 2 minus half to the power n, and this leads to 1.5 to the power n algorithm. And this is nothing special about vertex cover. In fact, it works for every subset problem. And in 2019, we read an article who said for interesting subset problem for which we can get a c power k n to the power big O of 1 parameterized algorithm, we can translate into an exact algorithm with running time 2 minus 1 by c to the power n. And it had so many corollaries, and this still remains a state of art for most of these problems. And it allowed two different fields to combine together into one and gave us an uniform way of designing algorithms from one paradigm to the other. And there's nothing special about graphs, except that I like them. But these kind of algorithms can be designed for all kinds of input, like point sets, set families, matrices, matroids, strings, number, probability distribution, you name it. And we have designed algorithms on these things, but we only stuck to a graph for this talk. But how do you know when to stop looking? So the way in polynomial time we prove a problem is NP complete, then we stop hoping to design a polynomial time algorithm. In approximation algorithm, we show a theorem like PCP theorem. Via PCP theorem, we show you cannot have certain constant factor approximation. Similarly, in parameterized algorithm, we show a problem is W1 hard, then we stop looking for these kind of algorithms, similarly, and so forth. So all these areas also have a well-developed lower bound theory to show when you cannot have such an algorithm. In fact, you can pinpoint what kind of algorithm, what form of running time you can have or you cannot have. And all these fields are interlinked, like approximation algorithm, parameterized algorithm, restricted input, exponential time. And currently, given a problem, people try all mix of these paradigms to come up with a solution which is useful and important. And this is the current state of art, where we are trying to mix all these kind of paradigms to solve a hard problems and help the users. And this is also just justified by the kind of lower bounds we are able to prove on these kind of problems, like in polynomial time as well as complexity theory, and they have some kind of bridging between them. So with this, I'd like to thank, and I'll be done with the talk. Thank you.